For centuries, sailors spoke of monstrous walls of water that appeared without warning, towering waves capable of snapping steel hulls and swallowing ships whole. Scientists dismissed these tales as exaggerations, but at the end of the 20th century, hard data proved them wrong. These waves are real, they are powerful, and they are far more common than once believed. Today we explore the true history of rogue waves, from early myths to satellite detections, from disasters at sea to the science racing to predict the next one. The story begins long before satellites or sensors, in logbooks and eyewitness accounts. In the 19th century, sailors often described walls of water rising from calm seas. One of the earliest known written reports came from the British ship Cleopatra in 1826, which recorded a towering sea like a mountain smashing over its deck. Through the late 1800s, reports continued. In 1861, a wave nearly 30 meters, 98 feet high, struck the Eagle Island Lighthouse in Ireland, shattering glass 60 meters, 197 feet above sea level. Storms couldn't explain it, and the wave never repeated. By the mid-20th century, survivors on North Atlantic shipping routes continued to describe single, enormous waves emerging from otherwise typical sea conditions. Without instruments, these stories remained anecdotal. The consensus in oceanography was firm. Such waves were statistically impossible. Then came the evidence. On January 1, 1995, the Draupner gas platform in the North Sea recorded a moment that changed marine science forever. During a moderate storm, a laser wave height sensor detected a single wave rising 25.6 meters, 84 feet, roughly twice the height predicted by existing models. The Draupner wave became the first instrumentally confirmed rogue wave in history. It wasn't legend or misperception. It was raw, measurable data. Engineers now knew the ocean could generate waves far beyond the limits used to design ships and oil rigs. After Draupner, researchers began re-examining historical records. They found hints that incidents once dismissed as freak accidents may have been rogue waves. This discovery triggered an international scientific effort to understand the phenomenon. In 2000, the European Space Agency launched the MaxWave project, analyzing 3 weeks of radar satellite data across the world's oceans. The results shocked the scientific community. In just 21 days, satellites detected 10 waves exceeding 25 meters, 82 feet in height. Rogue waves were no longer rare, once-in-a-century events. They were occurring regularly. Subsequent missions, including Envisat, confirmed similar findings and identified regions particularly prone to these extreme waves: the Agulhas Current off South Africa, the North Atlantic near Newfoundland and the Norwegian coast, and the Southern Ocean, where powerful storms circle Antarctica. These discoveries forced a rewrite of naval safety standards and forecasting assumptions. The ocean, it became clear, was far less predictable than previously believed. So how can such enormous waves suddenly form in a seemingly ordinary sea? Early theories focused on constructive interference, the idea that multiple waves can briefly align, combining their crests into a single giant peak. But later research showed this alone could not explain waves like Draupner. The real breakthrough came from nonlinear physics. In the early 2000s, oceanographers began applying equations adapted from quantum mechanics, particularly the nonlinear Schrödinger equation, to describe how energy moves within a wave field. Under specific conditions, energy can concentrate into one wave while draining neighboring waves, a process known as modulational instability. Another key factor is current wave interaction. When waves encounter strong opposing currents, their wavelengths shorten and their heights increase dramatically. The Agulhas Current, flowing east of South Africa, is one of the most dangerous examples. Here, powerful waves from the Southern Ocean collide head-on with fast surface currents, creating ideal conditions for rogue waves. It is no coincidence that this region has been linked to numerous maritime disasters. Advances in computational modeling also revealed that seabed topography and wind direction can further amplify local conditions, funneling energy into confined hotspots. In short, rogue waves are not random miracles. They represent the extreme edge of natural ocean dynamics, rare but explainable. Once science began taking rogue waves seriously, researchers revisited famous maritime tragedies. Several incidents once attributed to mysterious failures now show clear signs of rogue wave impacts. MS München, 1978. A German cargo ship vanished in the North Atlantic. Wreckage later revealed lifeboat davits bent downward 20 meters above the waterline, consistent with the impact of a single massive wave. Queen Elizabeth II, 1995. The luxury liner encountered a 29-meter, 95-foot wave south of Newfoundland. The captain described it as a great wall of water. Despite severe damage, the ship survived. Louis Majesty, 2010. A rogue wave struck the Mediterranean cruise ship near Spain, shattering windows and killing 2 passengers. Ucluelet wave, 2020. Off Vancouver Island, a buoy recorded a 17.6-meter, 57.7-foot wave in seas averaging only 6 meters, the largest proportional wave ever measured. Each event reinforced the same conclusion: rogue waves were not legends. They were part of modern ocean reality. Recent years have brought rapid progress in understanding and prediction. Oceanographers now use machine learning and high-resolution wave modeling to identify precursors to rogue waves. A team at the University of Maryland developed an algorithm capable of predicting rogue wave formation up to 5 minutes in advance by analyzing local wave interference patterns. Large-scale studies in the North Sea and Pacific have also revealed that rogue waves follow fat-tailed probability distributions, meaning extreme events are far more likely than traditional linear wave theory predicts. In 2023, researchers at the University of Victoria estimated that rogue waves can be expected somewhere in the global ocean every few days. That does not mean every ship will encounter one, but it confirms they are a persistent natural risk, not a once-in-a-lifetime anomaly. To improve forecasts, scientists now combine buoy data, radar altimetry, and computer models to generate real-time rogue wave risk maps. Prediction remains short-term, minutes or hours at best, but the shift is profound. What was once myth has become measurable, trackable, and, to a degree, predictable. The implications extend far beyond science. After Draupner, naval engineers began reassessing design standards for large ships, oil rigs, and wind turbines. Most vessels had been built to withstand a so-called 100-year wave of about 15 meters, 49 feet. Rogue waves can exceed 25 meters, exerting several times the force. Modern offshore structures now account for non-linear effects and site-specific risk. Simulation tanks in Norway, Japan, and Germany replicate rogue wave impacts to test hulls and platforms. Some navies have even begun using satellite monitoring to reroute vessels away from known high-risk zones, such as the Agulhas Current and the North Atlantic Storm Corridor. These adaptations reflect a crucial shift: acceptance that the impossible happens often enough to plan for it. In less than 3 decades, rogue waves have gone from legend to fact. They can form in any ocean. They can exceed 25 meters, taller than a 10-story building. They arise from non-linear dynamics and current interactions. They occur far more often than once believed. Above all, they show that even in the age of satellites and supercomputers, the ocean still keeps many of its secrets